A second traditional public health approach to communicable and non-communicable infections is the use of immunizations. Immunization refers to the strengthening of the immune system to prevent or control disease. Injections of antibodies may be administered to achieve passive immunity, which may provide effective short-term protection. Inactivated, dead, and live vaccines, attenuated live, can often stimulate the body's antibody production. Inactivated or dead vaccines utilize non-living organisms or antigens from an organism to develop antibodies to protect an individual from the disease. Live vaccines utilize living organisms that also stimulate cell-mediated immunity and produce long-term protection that more closely resemble the body's own response to infection. Vaccines, like medications, are rarely 100% effective and may produce side effects, including allergic reactions that can be life-threatening. Live vaccines have the potential to cause injury to a fetus and can themselves produce disease, particularly in those with reduced immunity. Some vaccines are not effective for the very young and the elderly. Therefore, the use of vaccines requires extensive investigations to define their effectiveness and safety, as well as to identify high-risk groups for whom they should be recommended. Ideally, vaccination occurs before exposure. However, when an outbreak occurs, vaccination of large numbers of potentially exposed individuals living in the surrounding area may be key to effective control. Thus, public health uses of vaccines need to include consideration of who should receive the vaccine, when it should be administered, and how it should be administered. Vaccine administration has traditionally been limited to injections as shots or ingestion as pills. New methods of administration, including nasal sprays, are now being developed. In addition, it is often possible to combine vaccines, increasing the ease of administration. Inactivated vaccines may not produce long-term immunity and may require follow-up vaccines or boosters. Thus, the use of vaccinations requires the development of a population health strategy that gives careful attention to who, when, and how.
In 1796, the scientist Edward Jenner injected material from a cowpox virus into an 8-year-old boy, with a hunch that this would provide the protection needed to save people from deadly outbreaks of the related smallpox virus. It was a success. The 8-year-old was inoculated against the disease, and this became the first ever vaccine. But why did it work? To understand how vaccines function, we need to know how the immune system defends us against contagious diseases in the first place. When foreign microbes invade us, the immune system triggers a series of responses in an attempt to identify and remove them from our bodies. The signs that this immune response is working are the coughing, sneezing, inflammation, and fever we experience, which work to trap, deter, and rid the body of threatening things like bacteria. These innate immune responses also trigger our second line of defense, called adaptive immunity. Special cells called B cells and T cells are recruited to fight microbes and also record information about them, creating a memory of what the invaders look like and how best to fight them. This know-how becomes handy if the same pathogen invades the body again. But despite this smart response, there's still a risk involved. The body takes time to learn how to respond to pathogens and to build up these defenses. And even then, if a body is too weak or young to fight back when it's invaded, it might face very serious risk if the pathogen is particularly severe. But what if we could prepare the body's immune response, readying it before someone even got ill? This is where vaccines come in. Using the same principles that the body uses to defend itself, scientists use vaccines to trigger the body's adaptive immune system without exposing humans to the full-strength disease. This has resulted in many vaccines, which each work uniquely, separated into many different types. First, we have live attenuated vaccines. These are made of the pathogen itself, but a much weaker and tamer version. Next, we have inactive vaccines, in which the pathogens have been killed. The weakening and inactivation in both types of vaccine ensures that pathogens don't develop into the full-blown disease. But just like a disease, they trigger an immune response, teaching the body to recognize an attack by making a profile of pathogens in preparation. The downside is that live attenuated vaccines can be difficult to make, and because they're live and quite powerful, people with weaker immune systems can't have them, while inactive vaccines don't create long-lasting immunity. Another type, the subunit vaccine, is only made from one part of the pathogen, called an antigen, the ingredient that actually triggers the immune response. By even further isolating specific components of antigens, like proteins or polysaccharides, these vaccines can prompt specific responses. Scientists are now building a whole new range of vaccines called DNA vaccines. For this variety, they isolate the very genes that make the specific antigens the body needs to trigger its immune response to specific pathogens. When injected into the human body, those genes instruct cells in the body to make the antigens. This causes a stronger immune response and prepares the body for any future threats. And because the vaccine only includes specific genetic material, it doesn't contain any other ingredients from the rest of the pathogen that could develop into the disease and harm the patient. If these vaccines become a success, we might be able to build more effective treatments for invasive pathogens in years to come. Just like Edward Jenner's amazing discovery spurred on modern medicine all those decades ago, continuing the development of vaccines might even allow us to treat diseases like HIV, malaria, or Ebola one day.
While vaccinations and immunizations are an important part of public health strategies to reduce the burden of infectious diseases, there are some individuals who are not able to get vaccinations due to compromised immune systems. These include the elderly, young children, and others who might have diseases that cause compromised immune systems. So what protects them from getting infectious diseases? It's a concept called herd immunity, and this short video that follows explains it in greater detail.
Vaccines help protect us from diseases that can potentially kill us, like measles, polio, and even the mumps. Even when people opt out of vaccines, they can still provide fringe benefits for the rest of us, especially for people who aren't eligible for certain vaccines, like pregnant women and infants. In fact, you can effectively eliminate a disease without vaccinating every person. But why would that be? The answer lies in something called herd immunity. When you hear herd, you may think of a clutch of cows, or maybe a band of buffalo. And we know that if a lion is closing in for the kill, a single buffalo may be safer because he's part of the herd. In a similar way, you are safer when most of the people around you have immunity to a disease. At its most basic level, think about how you get sick. When a contagious disease enters into an unvaccinated group, sickness can spread rapidly. This is because there's no immunity to the disease in the group. If most people, the herd, have been immunized, then you get some indirect protection. Thanks to them, it's less likely you'll come into contact with someone who has the virus. That's herd immunity at work. But when a larger number of people have no immunity, you're out of luck. You have less people to shield you. As early as the 19th century, a British epidemiologist named William Farr noticed this phenomenon with smallpox. Now it's recognized as a key tool to prevent disease outbreaks. So how many people must be vaccinated to keep you safe? It really depends on the disease. For measles, scientists think about 94% of the population. For other diseases like smallpox and diphtheria, scientists think it's closer to 85%. So that's why vaccines play such a central role in protecting populations. For once, it's best not to be special. Here's to being part of the herd. For Scientific American's Instant Egghead, I'm Dina Fine-Marin.